This is the first video of the structure of the atom. I'm going to just go over what an atom looks like and about the stability of an atom. Also within this, I'm going to talk about the periodic table, how to read the periodic table, because this will help you for future units. So first and foremost, just going to show you what this PowerPoint is going to cover. So it's going to cover 1.1 all the way to 2.2. And to start with, to ease you into chemistry, just want to cover a bit of the history of the atom. Okay, so you don't need to know this for the assignment, however, it's just a nice introduction into what we know now. So the definition of an atom is the smallest part of an element that can exist, and all substances are made of atoms. So water, air, they're all made up of atoms. And our understanding of an atom has changed over the years. At the beginning, it started with the solid sphere model, before moving into the plum pudding, then to the nuclear, then to the planetary. And so it all started with a chap called John Dalton. So Dalton's model is that an atom was just a solid sphere, like a bowling ball. So this was back in 1803, and he published a 3-part atomic theory, where all substances were made up of atoms. Atoms are small particles that cannot be created, divided, or destroyed. Atoms of the same element are exactly alike, and atoms of different elements are different. And the atoms join with other atoms to make new substances. Now, much of his theory was correct, however, some of it was proven incorrect later. And it was all through experimentation that we began to develop the model. So, a little experiment by J.J. Thomson. What he did was that he used a cathode ray tube. And through this experiment, he found that atoms can be divided into small parts. So what he found was, with the cathode ray tube, there is a beam of light, of electrons, and he found that by moving charged plates towards this beam and away from the beam would move. So instead of staying straight, it would move from left to right. And so from this, he found that particles must have a negative charge. So he proposed something called the plum pudding model, which is negative electrons scattered through this soft blob of positively charged material. Then Ernest Rutherford took it one step further. So in 1911, he shot beams of positively charged particles into a sheet of gold foil. Most particles continued in a straight line, which, as expected from the plum pudding model. However, some particles were deflected to the side, and some bounced straight back. And from this, he came up with a new model, which was that most of an atom's mass was found in a center region called the nucleus. In this model, the atom is mostly empty space, and this is where we begin to see that electrons travel in random parts around the nucleus. So this was his experiment. So on the left, this is the plum pudding model. So you can see the blue would be the positively charged blob with electrons scattered out throughout. And what he expected, so when he shot this positively charged beam, he expected it to go straight through or maybe curve just a little bit. But what he found through repetition was that when the beam would go through a certain section, they would bounce off to the side and come straight back. This was unexpected. So he thought that there must be something that is bouncing or deflecting the particles that are being shot. Then came Bohr. This is a model that we should recognise from GCSE. So this was 1913. This improved Rutherford's model using more maths. And he found that electrons, or at least he showed, that electrons occupy shells or energy levels around the nucleus rather than them randomly whizzing around this cloud. So, a little bit of a recap of what is in an atom. So in an atom we have protons, we have neutrons, we have electrons, we have a nucleus, and we have shells. So let's switch. There we are. So in an atom we have the center, and we have these rings. Now I am not an artist, however I do try. So from what we've just talked about, we know that this in the center is a nucleus. Okay, it's the center of an atom. And from Bohr, he showed that these rings that he called shells are energy levels. So within a nucleus, there are two kinds of particles. Okay. So pink, these are protons. Okay. And along with them, we have neutrons. I will build up on this, don't worry. And in the shells, we have the third subparticle. and these are negative. These are called electrons. Okay. So, to summarize, atoms are made up of two parts. We have the center, which is called a nucleus. Now, this nucleus is made up of protons and neutrons. And then we have the rings, or shells is the correct term. And this is where electrons live. Okay. Now we've talked about charge. Okay. These three subparticles do have different charges. Okay. So protons are positive. Okay. It rhymes. Protons are positive. Neutrons are neutral. And this is the only one that doesn't rhyme. Electrons are negative. Okay, so positive protons, neutral neutrons, negative electrons. And this is why I have put pluses and minuses around. Okay, so by knowing this, we can begin to see where the charge is being shared. Okay, so in our center, we have protons and neutrons. Well, protons are positive. So our nucleus is said to be positively charged. And this is because of the protons. Surrounding this positively charged nucleus, we have shells which contain electrons, and these are negatively charged. Okay. Now, when we have a positive and a negative, these draw each other together. So what's keeping the atom together is our positive center and our negative outline. So it's the negativity that's been drawn to our positive. It's literally what we call attraction. It is positive and negative attraction which is keeping the atom together. Okay. Now we've talked about charges. We have to now talk about mass. So let's switch back over. Okay. So we've talked about protons being positive. Now at GCSE, and we do stick with this throughout chemistry, protons have a relative charge of +1. Okay. They also have an associated mass, which is 1. Neutrons, they are neutral, so they have a relative charge of nil, of 0, but they have a relative mass of 1. So in terms of mass, you could also say size. Protons and neutrons have the same mass, they are the same size. Electrons have the equal and opposite charge to protons, -1. But their mass is considerably smaller. Now at GCSE, this is 1/2000. When we're going into A-level, level 3 and above, the relative mass is 1/1836. Now, one big question I am always asked is, why do we have relative? Why is it relative charge? Why is it relative mass? Well, to answer that question, we're going to need to watch a little video. And as with all things chemistry, it is not as straightforward as this has a charge of 1, this has a mass of 1. So when we take a look at the actual masses, and in terms of mass, we look at kilograms rather than grams, we can see that protons, neutrons, are extremely small. Okay, so this is to the power of -27. So what that means is, let me shift over. So if we take this number times 10 to the power -27, okay? Now what this means is that we've moved this decimal place 27 times that way, okay? So 1, 2, 3, 4, 5, 6. 20, 7, 6, 7, 3. That is how much one proton weighs. That is tiny, tiny, tiny. So what we do instead is that we compare their mass and their charges against each other. Okay, so just switching on back to this. So looking at this, we can see that these two numbers are the same. Okay, these two numbers are the same. So if we assign a proton to the mass of 1, because our neutron weighs the same, it's also going to be 1. As you can see, electrons are much, much smaller. This is why they are given the 1/2000 mass. Okay. Now, same goes for charge, and this is measured in coulombs. You can search by yourself about coulombs, but it's the same principle. We measure in relation to each other. We assign a proton a +1 charge. Electrons have equal and opposite charge, so they have a -1. Okay. So small recap. So within an atom, where is most of the mass? Where is most of the mass? Well, it's in the center. It is in the nucleus. Because we have a lot of protons, which are mass of 1, and neutrons, which have a mass of 1, Most of the mass is concentrated at the nucleus. Okay. Now moving on to mass number, okay? So this, we're bordering on to the periodic table and how to read the periodic table. But a mass number tells us the total number of protons and neutrons inside of a nucleus. So on the next slide I do have a periodic table, but let's just look at one of those little tiles, okay? So here we have the periodic table. Yes, I know it's not in English language, but we can take one of these squares, okay, one of these tiles, so to speak, and as you can see, there are numbers within it. So let's break down those numbers, shall we? Okay. So taking a look at sodium. Okay. So sodium within this tile has two numbers. It has the number 23 and the number 11. It will also have its symbol and its name. The biggest number is the relative mass number. The smaller number is what we call the atomic number. Okay. Important thing to note is that the atomic number tells us how many protons are in the nucleus. From this, we can work out the number of neutrons. Okay. So remember, relative mass is the total number of protons and neutrons in a nucleus. Atomic number is how many protons we have. So if we take the big number and, take the smaller number away from the bigger number, we'll get our number of neutrons. We can also figure out how many electrons are in the shells. Because atoms are neutral, whatever it states for the atomic number, you must have the same number of electrons in an atom. So in an atom, there is the same number of protons and electrons. Okay, just to reiterate, atoms are neutral. And we're going to start talking about charges. Okay. So when it comes to charging on atoms, they have no charge, they are neutral. They are not positively charged or negatively charged because the number of protons and the number of electrons balance out. Okay. So, over to you. You may want to take a look at a periodic table to help you. I know that I definitely will be. However, the first few should be, filling in the number of protons and electrons should be okay for the first few. Okay, let's go through the answers. So, oops, sorry, just moving things about. So the first row is done for us, which is carbon. Then we have hydrogen, so it's already told us that it has 1 proton and it has 0 neutrons. Well, in an atom, the number of protons must equal the number of electrons, so the answer to that one is 1. In fact, I might do it in a different colour. Okay. Same goes for calcium. So we're trying to find out the protons and the number of neutrons. Well, if we have 20 electrons, we're going to have 20 protons. But to work out the number of neutrons, we're going to have to look at a periodic table. So for calcium, its mass number is 40. Oops. Okay. So its mass number is 40. And we're going to take away its atomic number. So our answer should be 20 neutrons. Now iron, Fe, it's told us we've got 26 protons, so we must have the same number of electrons. Oh, I keep forgetting. Just highlight it. Just highlight it, that'll make sense, wouldn't it? There we go. There we go. Okay, so again, we need to look at the periodic table to figure out the number of neutrons. So it is mass number 55. You can round this up to 56 if you wish. Take away 26. Neutrons is 30. Or if you round it down, 29.85. Okay. Then fluorine, it's not given anything, so we're going to have to use the periodic table to find that. Okay. So fluorine has an atomic number of 9. It's an atom, so it must have the same number of electrons. And its mass number is 19. So it should have 10 neutrons. Okay. Now, whilst you were looking at that, you may be asking, why is some of the numbers, like for example iron, why are they not whole numbers? Why does it say 55.85? Why is it not a whole number? Well, this is where things start to get a little bit complicated. It's not that complicated, I promise. Let's switch over. So within natural Earth and space, we have different atoms, evidently, through the periodic table. However, some elements also have slightly different atoms within their group. And this is called an isotope. Okay, so an isotope is an atom which has the same number of protons but has different amount of neutrons. Okay. Now it's important to note here that the number of protons is unique to that element. It's what gives an element its identity. So atomic number, number of protons, gives the element, or the atom, sorry, its identity. So if an atom has 6 protons, it belongs to carbon. If it has 9 protons, it is fluorine. So let's take hydrogen for example. So typically a hydrogen atom, which is this first one in red, has one singular proton and one electron. You can see by comparing it to the others that it has no neutrons. It literally has one proton and an electron. Then we have deuterium, which has that additional neutron. And we can see that the mass number has changed from 1 to 2. Third, we have tritium, or tritium, which has 2 neutrons. So we can see it still has that one proton, but the number of neutrons has changed. We have loads of other examples. So for example, carbon. Carbon has many different isotopes. And yes, organic things may have carbon with extra neutrons in it. Carbon-13 does actually appear in organic things like us, or bananas, or medicines. Okay, it does not affect us in the slightest. But this is reflected in the periodic table. Okay, so take chlorine, which is 35.5. Because of the existence of isotopes, stable isotopes I should say, it is an average across these isotopes that gives us our atomic mass. Okay, so taking a look at a different example. This is oxygen. So in terms of stable oxygen, we have 3. All have the same proton number because it's oxygen. If it didn't have 8 protons, it wouldn't be oxygen. But we can see that the mass number is changing. So here we have 8, then we have 9, then we have 10. And throughout the universe, we have a different percentage. So this is how much naturally is in the world of each of these. So we have mostly, we have this one. Okay, oxygen with a mass of 16. Coming in behind that, we have a few which has the extra 2 neutrons, 18. And then we have a very, very, very small amount of oxygen, 17. Now there is a calculation that you can do. You don't need to know this. However, this is why it is not a nice, neat number. It's because of the presence and the existence of isotopes. Now, the extra neutrons within isotopes usually make their nuclei unstable. Usually, not always, there are exceptions to the rule. In order to become stable, elements, isotopes, will lose different particles from their nucleus to change or to release energy to make themselves more stable. This is where radioactivity comes from. So remember, the number of protons gives its identity. During radioactivity, atoms may lose neutrons and or protons, physically changing it into another element, emitting large amounts of energy. This process does happen randomly in nature. This is why we have background radiation. But it can be created by humans, for example, inside a nuclear reactor. And we know that radioactive elements exist as well. So you probably have all heard of uranium or plutonium. These are naturally radioactive materials. They are unstable and will undergo decay, is what we call, where, it will decay, it will give off radioactive substances to change itself into another element. So that is everything. That is everything for this first presentation. Okay, so to cover learning outcomes 1.1 to 2.2, we've covered the structure of an atom, what it contains, we've talked about the charge, we've talked about the mass, we've talked about isotopes, and we've talked about unstable isotopes. In the next PowerPoint, we're going to talk more about the shells and about electrons. Okay, so this first PowerPoint is mostly about the protons and neutrons. Next is all about electrons and shells. If you have any questions, feel free to pop them in the comments below, and I'll see you in the next one.